Good day everyone. Today we're going to discuss about the properties of definite integral. Now, in the previous discussion, we already discussed about the fundamental theorem of calculus. We use that in order to solve definite integrals. Now, this time, we're going to discuss one by one the properties of the definite integral, which are also very useful in order to solve the definite integral problems. So, here are the properties.
So here we have the properties of definite integral. We start with the first property. We have the order of integration. This is given by the integral of f of x dx evaluated from b to a is just equal to the negative of the integral of f of x dx evaluated from a to b. So this means that even if you're going to flip or interchange the lower limit and the upper limit, as long as we put negative or we multiply the integral of this by a negative 1, then these are just equal. So the geometric interpretation, suppose we have here a function y is equal to f of x, and we have also boundaries x is equal to a and x is equal to b, and we want to know the area of the region bounded by this curve, then we can use the formula or the property number 1. Number 2, the zero width interval. This is given by the integral of f of x dx evaluated from a to a is equal to 0. Okay, so what does it mean? Suppose we have y is equal to f of x and we want to know the integral of y is equal to f of x from a to a. So this means we are going to subtract a from a. So a minus a is equal to 0, meaning we have the width which is equal to 0. So therefore, we cannot form an area or we cannot find an area in this case. That's why the integral is equal to 0. The third one, we have the constant multiple rule. So this is given by the integral of k, where k is any constant, times f of x dx, evaluated from a to b, is just equal to k times the integral of f of x dx, evaluated from a to b. So we just only pull out the constant k, and this one becomes equal to this expression here. So here is the geometric interpretation. Suppose the given function is y is equal to f of x, okay, and there is a constant, let's say 2. So the constant k times f of x, or 2 times f of x, is this one. So it seems that the function y is equal to f of x is just being stretched out, okay? So the resulting definite integral is this area here, the whole area. Then the fourth one, we have here the sum and difference. So this is given by the integral of the sum and difference of the two functions f of x and g of x dx, evaluated from a to b. This is just equal to the integral of f of x dx, evaluated from a to b, plus or minus the integral of g of x dx, evaluated from a to b. So as you can see here, the definite integral of the sum and difference is just equal to the sum and difference of the integral. Okay? So here is the geometric interpretation. Suppose we have y is equal to f of x, the first function, and we also have the second function, which is y is equal to g of x. Then we also have the interval from a to b. So this area here, bounded by y is equal to f of x and x is equal to a and x is equal to b. And the area here, this is the area of the region bounded by y is equal to g of x, and x is equal to a and x is equal to b. Then if you are going to sum or to add this area and to this area, then the resulting area is this, the green one up to this. So this is how we use the sum and difference rule or the property. Okay, next is the additivity. So what is additivity? Additivity is given by this formula. This is the integral of f of x dx evaluated from a to b plus the integral of f of x dx evaluated from b to c is just equal to the integral of f of x dx evaluated from a to c. So we're just like splitting this, we just split the region into two, or we just divide the region into two. So this region here, the whole region is actually the definite integral of f of x dx evaluated from a to c. So to get the resulting definite integral from a to c, we can simply get the integral of f of x dx from a to b plus the integral of f of x dx from b to c. Okay, so we just simply add the two divisions. Then the next one, we have here the maximum minimum inequality. Now, if f has a maximum value denoted by max f and minimum value denoted by min f on a closed interval AB, then this inequality holds. Meaning, if you have a maximum value of the function and you also have the minimum value of the function, then the definite integral, this one, f of x dx, is less than or equal to the maximum of f, maximum value of f, times the interval, or b minus a. But this definite integral this is smaller than this, but this is greater than or equal to the minimum value times b minus a, or the interval. Okay, so we have here the geometric interpretation. So suppose this point here is the minimum value of the given function y is equal to f of x, because this is the graph of y is equal to f of x, and this is the minimum value. So we can have here, and we have here the maximum value of f. This is the maximum value, so we can create a horizontal line. So as you can see here, the definite integral of f of x dx is just less than or equal to the maximum value, which is the height of the function, times the interval, because we are comparing the area of this region here and also this area and also this area. So this means that the definite integral is just less than or equal to the maximum value of f times the interval, which is the width, but greater than or equal to the minimum value of the function times b minus a, which is the interval, because we are getting the area of each region. Okay, so next is the domination property. Suppose we are given a function which is greater than the other function. Let's say the function is f of x greater than or equal to g of x on a closed interval. So if this is our assumption, then it follows that the integral of f of x dx evaluated from a to b is also greater than or equal to the integral of g of x dx evaluated from a to b. Then, on a special case, suppose we are given a function f of x which is greater than or equal to 0 on a closed interval. then it also follows that the integral of f of x dx evaluated from a to b must also be greater than or equal to 0. Okay, this is the geometric interpretation. Suppose we have y is equal to g of x and we also y is equal to f of x. And since in this inequality, f of x is greater than or equal to g of x, so this is f of x greater than g of x on a closed interval ab in this case. So if that condition holds, then this also follows. Okay? And we have also here f of x which is greater than or equal to 0, meaning it's positive. Then it also follows that the definite integral of that must also be equal to or greater than or equal to 0. Okay, so these are the properties of the definite integral. So this time we are now ready to apply this property or properties. So we have here examples. So using the properties of the definite integral, we are given this problem or problems. So first, we are given that the integral of f of x dx evaluated from 1 to 3 is equal to 6. So we are only given a generic function, which is f of x. And the next one is we are given that the integral of f of x dx evaluated from 3 to 7 is equal to 9. Another given is the integral of g of x dx evaluated from 1 to 3 is equal to negative 4. So these are the given problems or the given information. So all we have to do from here, we can um, answer the problem using this given information. So for example, our problem is this one. The integral or the definite integral of 3 times f of x dx evaluated from 1 to 3. What's the answer? Applying the constant multiple rule, we have here 3, okay? 3 is constant, right? So we can apply the constant multiple rule. We can pull out the constant 3, okay, this one, and evaluate the integral of f of x dx evaluated from 1 to 3. And since from the given information here, okay, as you can see, this is just equal to what? This is just equal to 6. Therefore, if you know the answer of this definite integral, so you just simply multiply that one to the constant k, which is 3. So we have 3 times 6 is equal to 18. Next, so we have the definite integral of 2 times f of x minus 4 times g of x, okay, dx. So what properties are we going to use? There is a constant multiple, and we also have what? We also have the difference of the integral. So we just simply do like this. Since 2 is constant, so we can write 2 outside in this integral. Then f of x dx. And 4 is another constant. So applying the constant multiple rule, this one we write 4 outside in the integral. And since we already given that this one is equal to what? This is equal to 6. And this one, by the given information that we have, this is equal to what? This is equal to negative 4. So applying those properties, we have 2 times 6 is equal to 12 minus 4, which is 16. So we have 12 plus 16, which is equal to 28. Then the next one, we have the integral of f of x dx evaluated from 1 to 7. So from the given information, we don't have um, a given like this, right? But we have here, the given information here. This first one and the second one. Okay? So by additivity, because the problem is we are going to evaluate from 1 to 7. But the given information, we have a definite integral from 1 to 3 and 3 to 7. Okay? So by additivity, this becomes the integral of f of x dx evaluated from 1 to 3 plus the integral of f of x dx evaluated from 3 to 7 is simply equal to what? This is simply equal to 6 plus 9, which is equal to 15. Okay? So the next one, we have the integral of f of x dx evaluated from 3 to 1. How can we answer this one? We have to take note that we don't have a problem or the given information like this. But we can still solve this one using the property. What property? The first property, that is the by reversing the or interchanging the upper and the lower limit, then we put negative. We have to take note that the integral from 1 to 3 is equal to 6. So putting the negative and multiplying it to 6, we have. So this means that this expression here is just equal to the negative of the integral of f of x dx evaluated from 1 to 3. And since we know the integral of this is equal to 6. Therefore, we have negative times 6 or negative 6. Okay? So another example, we have here the integral of a constant c dx evaluated from a to b. So we just simply um, use the technique of integration or the fundamental theorem of calculus. We have to get the integral first or the antiderivative. So this is cx, right? Then we just simply follow the fundamental theorem of calculus. We just simply substitute our b in our x. So we have c times quantity b minus a, which is cb minus ca. Then the next one, we have the integral of x dx evaluated from a to b. Again, we just simply get the antiderivative. This is x squared over 2, right? Then applying the fundamental theorem of calculus, we substitute b. So this becomes b squared over 2 minus a squared over 2. Then the next one, we have the integral of x squared dx evaluated from a to b. This is equal to what? The antiderivative is equal to x cubed over 3, right? Then we just simply substitute the upper limit and the lower limit using the fundamental theorem of calculus. So this becomes b cubed over 3 minus a cubed over 3. Okay, so we apply this um, formulas or properties. So we have the integral of 4 dx. So how can we do this? 4 is a constant, so we can apply this one. So we just simply copy 4, then we just simply substitute 6 to our x. So this becomes 6 minus 2. We have 4 times 6 is equal to 24 minus 8 is equal to 16. Next one, we have x, integral of x dx evaluated from 4 to 8. So this is equal to x squared over 2. Simply substitute the upper limit and the lower limit. This becomes 8 squared over 2 minus 4 squared over 2. And that is equal to 32 minus 8, which is equal to 24. Next is the integral of x squared dx evaluated from 3 to 5. So what is the antiderivative? X cubed over 3. So simply substitute b cubed over 3, excuse me, minus 3 cubed over 3. We have the answer 32.67. Sorry. So here we have the definite integral of x squared plus 3x minus 2 dx evaluated from 3 to 4. So by using the sum and difference of integral, we have here the integral of x squared dx from 3 to 4 plus 3 times the integral of x dx from 3 to 4 minus the integral of 2 dx from 3 to 4. Then simplify, okay? Then we have the answer 20.83. Okay? So these are the examples of applying the properties of definite integral. So thank you so much. Hope you like this video and hope that you learn from this video. So just keep on sharing the learning that you've got from this video. Thank you and God bless.